In this video, I will explain the theory behind the inverse of a function. For examples, watch the next video. If you study which functions have inverses, the answer may depend on which course you are taking, calculus or linear algebra, for example. I want to explain the apparent contradiction. First, I will explain the more rigorous way to define the inverse of a function, and second, the conventions we normally use in calculus. I assume you have already watched the previous video where I defined functions in general. Otherwise, some of the notation I used won't make sense. The idea behind the inverse of a function is simple. Swap inputs and outputs. For example, here is a function. If I reverse all the arrows, this requires swapping the domain and the codomain, I get the inverse function. So this picture summarizes the concept of inverse function. Let's write down a definition. Let f be a function from a to b. Remember, this notation means that f is the name of the function, a is the domain, and b is the codomain. Then, its inverse is another function. We call this new function f inverse. We use the same letter with a -1 exponent. And the inverse swaps the domain and codomain with respect to the original function. Where the rule for f inverse is defined by this identity. X equals f inverse of y exactly when y equals f of x. That means literally swapping inputs and outputs. But of course I have to say when this is true. This must be true for all x in A and for all y in B. That's it. Well, assuming this is a function. Two things may go wrong. First, consider this function as an example. If I try to construct its inverse, it is not a function, because 6 does not get mapped to anything. So what is wrong with the original function? There is an element in the codomain that is not in the range. That's a problem. Let's give a name to the good functions, the ones that do not have this problem. We say that a function is surjective or onto, these two words are synonymous, when the range is the full codomain. We are going to need at least this property in order to have an inverse, but by itself it is not enough. What else may go wrong? Consider this other function. If I try to take its inverse, it is not a function either. This time the problem is the element 5. It gets mapped to two things by the inverse. So what is wrong with the original function? There are two different inputs that get mapped to the same output. That's also a problem. Let's give a name to the good functions, the ones that do not have this problem. I had already defined surjective. Now I will define a second concept. I say that a function f is injective or one-to-one. These two words are also synonymous when different inputs must map to different outputs. More formally, for every two elements x1 and x2 in the domain, if they are different, then f of x1 and f of x2 must also be different. It is also common to rewrite this in a different but equivalent way. Instead of saying that different inputs must produce different outputs, we can require that the same output must only come from the same input. I have identified the two problems I may encounter when trying to construct the inverse of a function, and we get a nice theorem. A function has an inverse if and only if it is both injective and surjective. This is the end of the theory if we want to be rigorous. In most math courses, for example in linear algebra, this is how you will study inverse functions. However, in calculus we take a shortcut. We add an extra convention and we entirely bypass the first of the two problems. Here is how. Let's look back at the first bad function. The problem here was the element 6. 6 is in the codomain, but not in the range. But 6 is kind of not doing anything? Why don't we simply remove it? Then the function will have an inverse. Of course, If I do this, I am modifying the function. Strictly speaking, the original function is not the same function if I remove 6. But let's pretend it is. What I am doing is shrinking the codomain to fit the range. Or even better, forget about the codomain entirely and work only with the range instead. In calculus, we almost always do this without even saying it explicitly. And that's why most calculus textbooks almost never use the words codomain or surjective. Just remember that in other areas of math, you will have to be more careful. So, when we talk about an inverse function in calculus, what do we mean? We still need to begin with a one-to-one or injective function. We are omitting the surjectivity condition, but the function still needs to be injective, otherwise there is no inverse function. Let's call its domain A and its range C. The range, not the codomain. Then the inverse is another function, I denote it with the same letter with a -1 exponent, that swaps the domain and range with the original function, and which is defined by the statement x equals f inverse of y exactly when y equals f of x. I need to say when for all x in A and for all y in C. This statement, which is the core of the definition of inverse function, can be written in other ways. I am thinking that f goes from A to C, and f inverse goes from C to A, exactly undoing what f does. So if I compose them, it should be like doing nothing. Indeed, if I start with an element x in A, I apply f to it, and then I apply f inverse to it, I should get back to x. And the same is true if I compose them in the other order. These two conditions at the bottom are equivalent to the condition at the top, and are an equivalent way to write the definition of inverse function. Alright, so far this has all been very theoretical. We need some examples. I will present them in the next video.